I will talk about a ground motion record selection approach based on multi-objective optimization. First, I want to talk about why we need to care about ground motion record selection and what are the key parameters that we need to pay attention to when we select ground motion records. Then I will explain the procedure that I'm proposing and how it works. Afterwards, we're going to look into how we can be efficient when we select ground motion records. I will explain what I mean by efficiency because this is a broad term. And then I will show some examples of ground motion record sets and how this procedure can work. Here are some examples of some ground motion records or in other words, accelerations of the ground during an earthquake. What we usually do in earthquake engineering is use these as input to a structural model in order to obtain some results, some structural responses. In order for our results to be meaningful, the loading input should be meaningful or reasonable. Let's see what this means. Here is another way of seeing a ground motion record. This is the elastic 5% damped spectrum of an earthquake record, and here is what a record set might look like. So in order to be able to see the attributes of this record set, we should statistically examine it. In other words, see at the medians and standard deviations at each period of this spectrum. So statistical treatment of the record set we might also want to think about that at each period we should expect that the spectral values will follow a log normal distribution. And so someone might say that for this record set to be meaningful, it should meet some targets. There are a number of targets that someone might think of, the uniform hazard spectrum or a conditional spectrum, but I won't focus on what should be used or what are the benefits of the one over the other, because at the end of the day, it doesn't really matter. The methodology to obtain a record to meet this target can be broken down into matching a median spectrum and the standard deviation spectrum. And this is what I'm going to present, how we can do that. So here's the procedure that I'm presenting, and as you might expect, it can match a target median spectrum and a standard deviation spectrum over a period range. On the first plot, you can see the target median spectrum and the record set that matches these objectives, and on the second one, you can see how it matches the standard deviation spectrum. And what I want to point out here is that since we're talking about multiple objectives, more than one objective, medians and standard deviations, we should expect to have more than one solution. And that's what the third plot shows. On the x-axis is the one objective meeting some median values, and on the other axis we can see meeting the other objective standard deviation values. And here are all the sets that fulfill these requirements. Now, what are the steps of the method? Pre-processing, processing, and post-processing. First, we have to define the targets and some user-specific criteria, some criteria on the seismic parameters, the moment magnitude, the site classification, and the focal distance. These are used to screen the initial pool of ground motion records. We use tens of thousands of ground motion records, but it's to our benefit to screen this initial pool into a smaller number, a couple of hundreds, for our selection. Then the processing phase. This is where the algorithm really takes place. This procedure is based on a genetic evolutionary algorithm, and I will explain what this means. It is based on the evolutionary concept or the notion of natural selection. Let me explain how this works. We start with an initial generation of candidate solutions and we test them against the objectives, matching medians and standard deviations. We iteratively progress until we find the right solution through three processes: selection, crossover, and mutation. And I will explain these with a binary problem. Selection is just simply selecting the best performing individuals out of our initial random candidate solution pool. So if we're talking about strings, parent 1 and parent 2 might be these two of the best performing strings on our solution. That's selection. Crossover is simply favoring these two individuals, parent 1 and parent 2, for reproduction. So their child will have the same parameters, the same characteristics or genes as the two parents. So the child will also be in favor of being in the next generation. And the final procedure is mutation, where we just simply select one solution, the parent, and we alter its characteristics, its genes. Let me say that selection and crossover are called convergence processes, while mutation is divergence process and helps us explore, make sure that we have the global minimum to our optimization problem. Okay, and then we have post-processing. As I said, we can have a number of solutions that meet our requirements equivalently. So we provide the user of this method some extra tools to assess these different results. We can have an input of some significant periods. For example, if we want to assess a group of buildings, we might have some periods of interest inside the period range. So we might want to rank our solutions depending on that. The same concept can be applied into seismological parameters. So we might have a main contributing scenario. So we might want to assess our different solutions depending on what the main contributing scenarios, earthquake scenarios are, in order to have the best record set for our analysis. And the final part is the statistical distribution matching. And I will explain this by looking how we can be efficient and how we can meet some statistical distributions through our method. This is the cumulative distribution that we should expect to have at each period. With the black line you can see the target, and my only point here is that we might meet medians and standard deviations, but the fit to the overall distribution might not be as good, especially if we have less numbers on our variable, as the blue sample here. What can we do to be efficient is take advantage of the technique called stratified sampling instead of the simple random generation of numbers. So, or you might be familiar with the term Latin hypercube sampling. So what this simply is just dividing the probability space into equal spaces. Here I did it for 10% probability spaces, and then obtaining the equivalent, corresponding subspaces on our variable. And we would ideally we would generate numbers randomly inside each of these subspaces. Of course, here we select ground motions. We don't generate values. We have to select recorded ground motions. So the equivalent to stratified sampling here would be to select ground motion records that their spectral accelerations fall into these bins, so that we can take advantage of the stratified sampling technique. I will refer to that requirement as the distribution matching efficiency requirement. And I will give you an example how the procedure and this requirement might work. Here you can see a spectrum with the red lines are the targets and the blue lines are the records, medians and standard deviations. On the top plot you can see how the fit is on the percentiles 16th, 15th and 50 and 84th percentile. And on the lower graph you can see the dispersion spectrum and how the match is being accomplished there. And I will show how this requirement might provide differences in these two periods, let's say, of interest. We might be interested in t equal to 1 second or t equal to 2 seconds, and I'm just going to show if this efficiency requirement improves our results. Here we just compare target distribution functions with empirical distribution functions, so to see if our results are matching what the target should be. On the left side, you're going to see the periods at 1 second. On the right side, you're going to see the periods at 2 seconds. And the first row is when the efficiency requirement was asked only for 1 second. The second row is when it was asked only for 2 seconds, period. And the final row is when I required it for both. And the only argument here is that when the distribution matching requirement was performed, the distribution matching is much better than when it wasn't required. So it gives us a notion that stratified sampling can improve our efficiency in ground motion selection, so that we can have less ground motions with better efficiency. And now here's an example of a ground motion record set. This example is when the target spectrum is the Eurocode spectrum, and it's a case study. It's about, for example, I took some parameters for seismicity in Vienna and how this would work. The Eurocode currently says that we have to think about the range of 0.2 T1 to 2 T1, T1 being the period, the first eigenperiod of our structure. And if we want to have a ground motion record set for an asset of buildings for a region around Vienna, for example, mid-rise concrete or reinforced masonry buildings, the range of periods might be way too big then, and from 0.1 to 4 seconds, we can see how we can have spectra and spectra matching and our records matching these spectra. I have two different target requirements. With the red lines, you're going to see the target spectrum of the Eurocode. The black dashed lines are the boundaries. On the left side, we have upper and lower bounds, and the median of our spectra, of our records that we're going to select should fall into 0.75 and 1.35, the ratio of our median to the Eurocode spectrum. And on the right side, all of our records should not fall below 90% of the target. And these are pretty hard requirements that the Eurocode currently asks. So I just wanted to show this example in order to show the versatility of the algorithm and how the targets can change and have results for different kind of requirements. And here are the conclusions. The algorithm can be efficient for complex optimization problems such as ground motion record selection, and in order to avoid sequential searches, and this is pretty important as ground motion record sets, data sets are increasing with time. How the provided algorithm or methodology can meet arbitrary targets in first and second order statistics is the key to any ground motion selection, and how we can increase efficiency. That was the overview of the methodology and my presentation, and a little bit about the challenges and the next steps. We should a little bit improve how the genetic algorithm works in order to make it a little bit adjustable on the specific problem. So if different targets need to be met, maybe the algorithm can work even better on selecting the ground motion records, and also include some other statistical requirements that might be of interest, such as correlation control. Thank you very much.